So this is part 2 of chapter 6. I left off here from the last part 1, so we're going to move forward. In terms of effect of substituents on the rates of SN2 reactions, here's an example of table 6.5, in which it shows that the methyl is the fastest, followed by primary, and then secondary, and then when we get to tertiary, it's really, really slow. And then in comparison of other primary, these are another set of primary alkyl halides or alkyl bromides, in which you're starting off with butyl, rate is pretty fast. Isobutyl, now it's getting bulkier. Over here, it starts to decrease, and neopentyl, although it's not tertiary, you're really losing reactivity. There are steric effects of the substrate on SN2 reaction. In general, the nucleophile comes from the backside of the carbon, and then it undergoes a ring flip or Walden inversion, which we'll talk about in a bit. And so it must overlap the backload of the CX sp3 orbital right here. And so as you go from primary, which is easy, secondary, now it's getting bulkier, but attack is possible. But if you look at this tertiary butyl bromide, it completely blocks nucleophile coming in. As a result, this is not possible, and SN2 does not occur. As I mentioned before, SN2 reactions will result in an inversion of a configuration, also known as the Walden inversion. This is terminology that you're going to have to memorize. Here again, this is hydroxide. It's attacking, and you have kick off of the bromide. It starts off with S2 bromobutane. Here's the transition state, again in brackets, double dagger, negative charge. You're getting this dotted line, so it's happening where the hydroxide's coming out as Br is being kicked out. Now you generate R, so you have an inversion of stereochemistry of butanol and bromine. Here's a molecular orbital diagram of how backside attack can occur in SN2. Here's the hydroxide. Here's that attack on the CBr, sp3 orbital. You're forming it. Here's a transition state. Again, double dagger, negative charge, and now you have this continuum shown here. And then the product. So you now took this and then flipped it on the other side. And this is shown nice as this umbrella model for the Walden inversion, in which you have attack come off, and now you've inverted the stereochemistry with a Br. In general, R and S are just names, so don't rely on the name to determine the stereochemistry of the reaction. In contrast to SN2, as we've discussed, SN1 over here is a unimolecular nucleophilic substitution. As a result, its rate is just dependent on the K, or the rate constant, as well as just the concentration of the alkyl halide. It undergoes a carbocation intermediate, something that is crucial, that is very different from SN2 reaction. And as a result of the fact that it undergoes carbocation intermediates, racemization occurs. In terms of the SN1 mechanism, the first step is the carbocation. So the carbocation is first formed by just spontaneous dissociation of the halide. Now it generates the carbocation R+ and the halide. The thing that I'd like to note are that in the case of SN2 reactions, the arrows are always going in one direction. In SN1 as well as E1, as I'll show you later on in this chapter, it has equilibrium arrows in which you have arrows going to the left and arrows going to the right. And the arrow going to the left is actually much larger than the arrow going to the right. So please note that when you're drawing reaction mechanisms that involve carbocation, I'd like you to use equilibrium arrows as shown here, and more precisely to use the left-handed arrow being much larger than the right-handed arrow. Then there's a second step. In the second step, you have the nucleophile come in, attack that carbocation, generating the bond. In this case, in the second step, this is in one direction. The first step, again, is in equilibrium. This is the rate-determining step. Here, once that rate-determining step happens, the rest is fast. So if a nucleophile is uncharged molecule, like water or alcohol, positively charged product must lose a proton to give a final uncharged product. Show you an example. Here's your tertiary alkyl iodide. The first step of SN1, like I told you, is, again, the spontaneous leaving of the leaving group, generating your carbocation. In this case, again, it's an equilibrium arrow, so please make sure you draw that in your answers when you have an exam. Again, the arrow going to your left is much larger than the arrow going to your right. Again, carbocation is the rate-determining step. The second part of the mechanism, here you're having attack. So now, because it's not, it's a neutral molecule, so it's neutral, CH3OH, you're going to have attack of the electrons from the oxygen come and then form. And because that is happening, again, here you have equilibrium arrows in which now it's really preferred going to the right. It's not just one arrow going to the right because now you're not using I guess a negatively charged molecule to quench that positive charge. Rather, it's a neutral molecule. So as in the previous case when I showed just one arrow going to the right, that was just in the cases of a negatively charged molecule coming in. For neutral charges, you're going to have still equilibrium arrows. So please note that. That's very important. So you have this formation of the alcohol, the ether, but it's positively charged, so you need a step. And that next step is having it pluck off that hydrogen, neutralizing the charge, generating the product. Here it's under equilibrium. The arrows are here equal. Now our product is neutral, and then you have a protonated methanol. The SN1 energy diagram has then three kind of energy states. One in which you start off with Rx plus nucleophile. Here's your intermediate, right? You form your carbocation. And then your product in which you've now done the switch. So there are two steps, right? The first step is carbocation formation. Here you have a big energy of activation, right? I can draw it out here. From your starting material to that first transition state. Again, this transition states are double dagger. This is labeled transition state 1. Then once you get to the intermediate, which is higher in energy and endothermic, then the carbocation then gets reacted by the nucleophile. Here you have a lower activation energy shown here, and then you're getting to a product that is more stable and lower in energy. And this is a fast step. Rates of SN1 reactions, so the order of reactivity follows the stability of carbocation, so it's opposite that to that of SN2. So we're looking at tertiary is more stable, followed by secondary, primary, and then methyl. So more stable carbocations require less energy to form, and a better leaving group will increase the rate of reaction. So if we look at solvation effects, the best types of solvents that you want to use for SN1 reaction are going to be polar protic solvents. And the reason why is because it's going to be able to stabilize both the cation as well as the anion, as shown here with an alcohol with the cation and anion. And then in terms of the structure of the carbocations are sp2 hybridized, and we've talked about that before, as well as being trigonal planar. So the lobes of the empty p orbital are both sides of that trigonal planar conformation. So after it releases, again, the equilibrium arrows, you're going to have Br minus, here's the empty p orbital. Now you can have attack of, in this case, ethanol on the top, deprotonation, and then you go from S to S. This is retention of configuration. If you've got attack on the bottom, and deprotonation, you're inverting the configuration from S to R. So because you can have the possibility of attack on both sides, again, you're going to get mixtures. This is just explaining the carbocation stability. Again, we've discussed that tertiary is preferred over secondary, primary, and methyl. Carbocations are stabilized by this inductive effect provided by the methyl groups onto that carbocation, as well as through hyperconjugation into the empty p orbital by the CH bond. In terms of the stereochemistry, here's an example of secondary bromide in SN1 reaction. So shown here, you have kickoff or leaving of the leaving group, again highlighting that these are equilibrium arrows in which the arrow to the left is preferred or larger than the arrow going to the right. This generates an empty p orbital and a carbocation as shown here, and bromine hanging out. Now you can have front side attack, right, of which the methanol oxygen comes and attacks the top, or attack from the bottom. If you get attack from the top, you're going to generate the bond. Again, it's protonated and positively charged, so then you have the oxygen of methanol and solvent, plucking off that hydrogen, quenching that positive charge, forming the product shown here. Same thing if you have it attack in the bottom, pluck that off, you get trans versus cis, in which there's a little bit more inversion, 60% versus the 40%. Again, the things to note here are the equilibrium arrows, again. In this case, once you start using the neutral molecule to attack, the arrows to the right are more, but again, make sure you show both arrows in which the longer arrow is going to the right. And in this case, this is a fast step, so the arrow is just going to the right. Rearrangement. So rearrangements can also happen because carbon cations can rearrange to form the most stable carbocation. So here's an example of 2-bromo-3-methylbutane. If it does a regular SN1 reaction, you're just having substitution of the bromine with ethoxide. This is an unrearranged product. The other thing that can happen is you can have, after the carbocation forms right here, you can have a shift, either a hydride or a methyl shift, in which here the hydride goes across. This generates a more stable cation from primary to looks like tertiary, and then as a result you can have that cation being attacked by the nucleophile to generate the product, and this would be the product. So you can do two types of shift. I had said in this case this hydrogen becomes shifted, this one over here, and this gets moved across after it forms this carbocation. So hydride shift, you have the hydride on the adjacent carbon that moves, or you can have a methyl shift in which the methyl on the adjacent. So if we look at an example, here's an example of a methyl shift in which bromine comes off, but in addition, the methyl group moves across, forming a carbocation over here. And as a result, there's this rearrangement. So in this case, since the primary carbocation cannot form the methyl group on the adjacent carbon will move, which is what happens here, to that primary carbon, displacing the bromide and forming that tertiary carbocation. Smallest group on the adjacent carbon will move. So if there is a hydrogen, this is really important, it will give a hydride shift over a methyl group because it's a smaller group that's moving. So if we compare SN1 versus SN2 and figure out conditions for SN1 and SN2 and compare them, here's a comparison table. In the case of SN2, methyl halides are preferred over primary over secondary. SN1, it's the opposite, tertiary, then followed by secondary. Requires strong nucleophile. Weak nucleophile is used for SN1 and may be also used as solvent. SN2 prefers polar aprotic solvent. SN1, polar protic solvents. So that is to solubilize the cation and the anionic halide. Rate is bimolecular, SN, that's why it's called SN2. So it's dependent on not only the rate constant, but the concentration of the alkyl halide as well as nucleophile. In the case of SN1, because it's unimolecular, it's only dependent on K and the concentration of the alkyl halide. SN2 undergoes Walden inversion. That's really important, and that terminology is something that you have to memorize, while as SN1 undergoes racemization in this case. And then SN2, there are no rearrangements. Rather, in SN1, you can see rearranged products. Elimination is the other portion that can happen, other type of reaction that can happen. Elimination falls under two types of categories, E1 and E2. In the case of E1, you form that carbocation under equilibrium conditions. So again, you have that arrow going forward and back, in which you have your backwards arrow is mostly preferred, and this is the rate determining step. Then you have the solvent come in, pluck off that hydrogen, form a double bond, forming the alkene and the protonated solvent. In the case of E2, this is all concerted, just like SN2 was concerted, in which now your alkoxide will pluck off that hydrogen, will form the double bond, and at the same time kick out the bromine, and then you'll generate your alkene, etc. So elimination in general forms double bonds, and it's also called dehydrohalogenation. E1 reaction is unimolecular, that's why it's E1. Two groups are lost, a hydrogen and a halide. The nucleophile acts as a base, so anytime you have elimination, you're going to have basic bases involved. And the E1 and S1 reactions have the same conditions, so a mixture of products will be obtained. So if you're going to have E1, S1 will likely occur, and so you're going to get a mixture of both elimination products as well as substitute products. So the mechanism. Again, the first step in the mechanism is kickoff of the halide. Again, that's under equilibrium conditions shown here. Again, so like in SN1, you have the arrow to the left going, being a little larger than going to the right, forming the carbocation and the halide. Second part is that the solvent, or the nucleophile, in this case it's a base, will deprotonate, form the double bond, generating the alkene and protonated base. Again, here is that equilibrium arrows. Now in this case, the arrow going to the right is favored. If you look at it a bit closer, you're starting off with a your base, and it's going to deprotonate the hydrogen. There's overlap with the empty p orbital shown here. and formation of that double bond and protonated base. Energy diagram akin to SN1 reaction, you're going to have three states. You're starting, your intermediate, and then your product. And the first step is going from your starting material to the carbocation shown above here. That first transition state is the rate determining step. It has a higher activation energy, and it's endothermic because it's higher in energy. And then you have the second step, which is lower in activation energy, and then also more stable. The product is more stable, shown here. Again, it's unimolecular, so reaction rate is just dependent on the alkyl halide. Carbocation formation is the rate determining step for this reaction as well as that SN1 reaction. So there are, nomenclatures for double bond substitutions. When you have all four things attached to the double bond, the carbons across the double bonds, this is called tetrasubstituted. If only three of them and the remainder is a hydrogen, this is a trisubstituted. This is di and this is mono, and the stability of the double bond follows as such, where the tetra is more stable than tri, more stable than di, more stable than mono. In elimination reactions, the major product of the reaction is the more substituted double bond. This is called the Zaitsev rule. Again, this is a name that you're going to just have to memorize, like Walden inversion. In this case, Zaitsev rules are applicable for elimination reactions. So if more than one elimination product is possible, the most substituted alkene is the major product, as it's most stable. So here's an example where you can have this ethanol pluck off either this hydrogen and form a double bond, or this hydrogen and form a double bond. If it does this hydrogen, it'll form trisubstituted alkene. If it takes this one off, it'll form just a disubstituted alkene. So this one is your major product that is full. E1 competes with SN1. So if we look at a reaction of a tertiary bromide, shown here, tert-butyl bromide, in the presence of ethanol and heat, you're going to get elimination as well as SN1. And so in general, the substitution results from nucleophilic attack of the carbocation, and ethanol serves as a base in the elimination as a nucleophile in the substitution, generating these two products. A carbocation can, 1, react with its own leaving group to return to the reactant, 2, react with a nucleophile to form a substitution product, SN1, 3, lose a proton to form an elimination product, E1, and 4, rearrange to give a more stable carbocation, then react further. E2 reaction, by contrast to E1, because it's labeled 2, it's bimolecular. It is an elimination reaction. This requires a strong base, and it is a concerted reaction. This is really important. So like SN2 are concerted reactions, E2 are a concerted reaction, and it actually requires a anticoplanar conformation, which we'll talk about in the next couple of slides. But it will happen where the proton is abstracted, double bond forms, and the leaving group leaves, all in a single step. So here's the E2 mechanism. Here's your strong base, plucks off the hydrogen, forms a double bond and kicks this off. Sorry, so you're missing this coming off. And so it has an intermediate. Here's a double jagged transition state, not intermediate, I'm sorry, which the base is coming off, forming the double bond and kicking this out. This forms the product, which is a double bond, protonated base, and the halide. Order of reactivity for alkyl halides, tertiary, followed by secondary, followed by primary. And then in terms of types of alkenes that are formed, you might form mixtures, but Zaitsev products will predominate. So just as in E1 elimination mechanisms, you have Zaitsev products being preferred, so do you have this the case being in E2. Now I mentioned this before, the alkyl halide of the proton, the halide and the proton to be abstracted must be anticoplanar. This is a word that you have to memorize, in which the angles 180 to each other for the elimination to occur. And I'll show you that as an example. The 180 meaning anti, and that I'll show you in terms of Newman projections. Orbitals of the hydrogen atom and the halide must be aligned so that they can begin to form the pi bond in the transition state. Anticoplanar arrangements minimize any steric hindrance between the base and the. So like I said, anticoplanar is when you have theta being 180, hydrogen is up here, and X is over here. So this 180 degrees is with respect to the hydrogen and the halide, and so they are anti to each other. If we're looking at the conformation, their base is going to pluck off. This is going to start to form that pi bond overlap. This gets kicked off, generating this. If it's not, if you compare it to the other conformation, syn coplanar, in which you're overlapping and you're seeing eclipsed interactions, where the hydrogen and the halide are right on top of one another. If a base comes along here, tries to pluck that off, you're going to get repulsion with the halide. So this is unlikely to occur in forming the alkene. So this is not that'll happen. So if we compare E1 and E2 mechanisms, both of them prefers the tertiary over the secondary, while E1 the base strength is unimportant. Usually it's weak. E2 requires a strong base. A good ionizing solvent is really necessary to stabilize that carbocation as well as the halide, whereas the solvent polarity is important for E2. In E1, it's unimolecular, so it's dependent on the concentration of alkyl halide. In E2, it's bimolecular. You have it dependent on the concentration of alkyl halide as well as the base. Both have a preference for Zaitsev products. There's no required geometry, but coplanar, anticoplanar is essential for E2 mechanism. You can have rearrangement products because of the formation of carbocations in the case of E1, but there are no rearrangements for E2. Substitution or elimination, if we're going to compare when will you have substitution or when will you have elimination. So the strength of the nucleophile determines the order. So strong nucleophiles or bases promote bimolecular reactions, so that you have SN2 and E2 being preferred when you have a strong nucleophile for SN2 or a strong base for E2. Primary halides undergo SN2. So whenever you see a primary halide and a good nucleophile, you're going to say that's going to go SN2. Tertiary halides are a mixture of SN1, E1, or even E2. They cannot undergo SN2. So please note that. High temperature favors elimination, and bulky bases favors elimination. So secondary alkyl halides. Secondary alkyl halides are challenging. So if you have strong nucleophiles, it will promote SN2E2. So this is key. If you have weak nucleophiles, it'll promote SN1E1. Strong nucleophiles with limited basicity favors SN2, and bromide and iodide are good examples of these. So here's an example in which you have strong nucleophile on a secondary bromide. So this will undergo E2 or SN2. In the case of a weak nucleophile as this methanol, you're going to have it undergo E1 or SN2. Okay. So this is one problem. You're asked to predict the mechanism and products for the following reaction. So the first step is that the bromine will come off. So before I do that, let me zoom in. Oops, sorry. Let's move this up a bit. And let's see if I can, zoom in a bit so that I can draw some arrows for you guys. Okay. So the first step here is the kickoff of the halide so that you form the carbocation. Really important, again, is the the arrows, the equilibrium arrows. Once the carbocation forms, it can undergo either E1 or SN1 because we're using weak base in this case. So if it undergoes E1 elimination, let's show, here's your hydrogen, sorry. So you're having electrons from that oxygen pluck off that hydrogen and then form the double bond, sorry. That'll generate this major product. The other possibility is that it can pluck off the hydrogen that's off of this methyl group. So this will pluck that off, and then double bond will forming this, which is the minor, because it's the least substituted. So the Zaitsev product is favored, and so you have to denote which one's going to be major versus minor. And then if it's the other case, I'm sorry, this is not as beautiful looking, you can have, I'm going to show it in blue, it undergo SN1, in which it directly attacks that carbocation, generating the SN1 product. Oops, sorry. I'm going to erase that. Okay, so that's so now I've shown you the arrows. You should show all the arrows in the mechanism because that's what it's asking, and I'm showing that over here. So here's the second problem in which you're asked to predict the mechanism and products for the following reaction. This is a secondary alkyl halide in the presence of sodium ethoxide and methanol. So this is a strong base slash nucleophile, actually a strong base. So you can have E2, but also competition with SN2 is occurring. I'm not showing you the mechanism based on the work before. You should be able to draw out a mechanism. And if you have any questions, just let me know and I'll be happy to answer them. But just in light of time, it can form the substituted product. You can have this hydrogen being plucked off and kicked off, generating the double bond here. This will be the least substituted alkene. Or you can have the hydrogen being plucked off from here, forming the double bond, kicking this off, forming the more substituted alkene. So this is obeying Zaitsev rule, where this is major versus minor. Or you can have simply nucleophilic attack on that carbon and kick off of the bromine, generating the substituted product. Now, if this is a chiral center, actually, this carbon, but the chirality is not noted. But if it was noted, then you'd have to undergo Walden inversion, and so show that if this was R, this turned into S. So please note that. And so this concludes chapter 6.